So for today's Do Now, there are two questions, both on cell potentials. Number one was actually a multiple choice question that I just turned into short answer. So this was right off of one of the practice multiple choice tests. And then number two is a question more out of the textbook, which is why it says use Appendix E. So remember, on a test or on a quiz, you will be given reduction potentials in a table like this. So if you ever need reduction potentials on a test or on a quiz, you're going to be given those in a table because that's what it will be like on the AP test as well. So for number one, based on the standard reduction potentials in the table above, what is the value of E naught for a standard galvanic cell made with silver and silver plus and chromium 3 plus half cells? So I want to look at one thing first. Remember, galvanic and voltaic, those mean the same thing. They always need a positive E cell. They're always spontaneous, so they need a positive value of E naught cell. Now, when we have these half reactions, question is always, well, we're not given the cell. How do we know what is reduced and what is oxidized if they don't tell us? These are reduction potentials. So these are both reduction potentials. This is the potential of something to be reduced. The higher your value of the reduction potential, the more positive the value, the more likely it is to be reduced. The less positive or the more negative the value, smaller the value, the more likely it is to be oxidized. So based on this, silver plus, right, Ag plus going to Ag has a reduction potential of 0.08. The other one is negative. So Ag plus is most likely to be reduced because Cr3 plus to Cr has a negative reduction potential. That really, Cr3 plus does not want to be reduced. Instead, we would expect to see Cr be oxidized. So this top one is more likely to be reduced because of the higher reduction potential. The second half reaction, we would expect to be oxidation. But if it's oxidation, we have to flip the reaction. So we flip the half reaction for it to be Cr solid yields Cr3 plus 3 electrons because that's oxidation, right? Oxidation number of 0 to +3. So when we want to determine the value of E cell, remember E cell is the reduction half reaction plus the oxidation half reaction. The only thing you can ever do to a reduction potential, so to calculate the cell potential, you do reduction plus oxidation. The only thing you can ever do to a value of E naught is flip the sign. You never multiply. That's why it doesn't even matter if we have to multiply these to get them equal. The only thing you ever do to a potential is change the sign. So the reduction half reaction is going to stay 0.080 volts because that is the reduction potential. That's the reduction half reaction. Plus the oxidation half reaction. Now, since we flipped this second half reaction because it's oxidation, we flip the sign. 0.41 volts. So since we flipped the Cr to Cr3 plus half reaction, we flip the sign. We change it from negative to positive. And so we have 0.08 volts plus 0.41 volts. I can't do this without a calculator this early. Oh, I could have. We get 0.49 volts. So the biggest thing is when you're given reduction potentials, remember the more positive the reduction potential, the more likely that substance is to be reduced. The more negative, so the smaller the reduction potential, the less likely it is to be reduced, and the more likely the product is to be oxidized. So that means that Cr, when we flip this, Cr becomes the reactant, and it's Cr yields Cr3 plus 3 electrons. So for number 2, a voltaic cell is based on these 2 standard half reactions. Notice these are both reduction half reactions. 2 plus down to 0, 2 plus down to 0. So these are the reduction half reactions. You're given the reduction half reactions because this says use Appendix E. So Appendix E was this white sheet. Remember that Appendix E is in alphabetical order. So what I want to do is I want to use Appendix E to find the reduction potentials for both of these half reactions. Now be careful because a lot of metals can have multiple oxidation numbers. So for cadmium, I'll go kind of halfway down the first row. I see Cd2 plus 2 electrons yields Cd solid. That reduction potential is negative 0.403 volts. And then we go to tin. Now, if you notice, there's 2 tin reduction half reactions on Appendix E. We're almost at the very bottom of the second column. We want the first one. We want SN2 plus to SN. So SN2 plus to SN is negative 0.136. Now notice these are both negative. So neither one of these really want to be reduced. But a voltaic cell has to have an oxidation half reaction and a reduction half reaction. So you need to figure out, and a lot of times I see people writing a note on the side, the more positive, more likely to be reduced. So the more positive the value, the more likely the substance is to be reduced. This you have to think a little bit. Really think about which one of them is closer to 0. Because the one that's closer to 0 is the one that's more positive. This 0.136 is actually closer to 0. That's the less negative of the 2. So this SN2 plus to SN actually has the higher, the more positive reduction potential. So SN2 plus is the one that will be reduced. You have to have a reduction half reaction and an oxidation half reaction. You have to. So that means that the Cd2 plus and Cd will be oxidized, which means when we want to look at the overall reaction, this reaction will be flipped in order for us to see the oxidation. Oxidation would be going from Cd to Cd2 plus because oxidation numbers are going from 0 to +2. So for part A, which half reaction occurs at the cathode, which occurs at the anode, so this is letting us review voltaic cells a little bit more. Remember that the cathode is where reduction takes place. The anode is where oxidation takes place. So yesterday I said that we're going to have a quiz. Tomorrow it's all multiple choice. We'll have a quiz on 10.5 to 10.7. So that's thinking about what's the cathode, what's the anode, what occurs at each electrode, which way do electrons flow, what about the salt bridge? And then 10.7 is calculating cell potential like we're doing now. So the cathode is reduction. So the half reaction that occurs at the cathode is SN2 plus 2 electrons yields SN. It's the reduction half reaction. So we have tin 2 plus turning into solid tin, which will stick to the cathode, which is why the cathode increases in mass. The anode is oxidation. Remember, this half reaction represents reduction. We are reducing the oxidation numbers. So if we want to show the oxidation half reaction, we flip it. So the anode is solid cadmium, creating cadmium 2 plus 2 electrons. And so at the anode, the solid cadmium is turning into cadmium ions and falling into solution, which is why the anode decreases in mass. So here's part A, the two half reactions that are occurring at each electrode. And then for part B, calculate the standard cell potential. So just like we did in number 1, cell potential is E naught cell equals the reduction plus the oxidation. So reduction, we leave alone. Right? This was the reduction potential. So negative 0.136 plus the oxidation. Now, because we flipped the reaction to represent oxidation, we flip the sign. The only thing you do to E is flip the sign. So plus 0.403. So if we plug this into our calculator, negative 0.136 plus 0.403, we get positive 0.267. And cell potential is measured in volts. Notice how we have a positive cell potential. That's good because this is a voltaic cell. Voltaic cell always has a positive cell potential. So if you were to calculate this and you were to get a negative cell potential, that should tell you, oh, I flipped them. That means you had your reduction and your oxidation half reactions backwards. Any questions on the do now? So if not, just a couple quick things. I posted during 5th period yesterday on Classroom about the review session. So Saturday and then in 2 weeks. All the information is on there, 10 points per session for attending and participating. So you can read all of that information on the stream of Classroom. And then tomorrow, we'll just do a short electrochem quiz just over the first half of electrochem, 10.5 to 10.7. Those are the 3 videos. Nothing for what we're talking about today. Nothing that we're going to talk about tomorrow, right? Just those 3. So what we did before break, and then what we did with cell potential, kind of like what we did in the do now today as well. Yeah.
You know what we talked about? I don't know if you know what I'm talking about, but when we talked about the mass, like you kind of drew it in.
Yes.
Like, you need to know that for the test or for the quiz.
Yeah, I mean, you want to know that the cathode will increase in mass and the anode will decrease in mass. So you want to know how the masses change as well.
Okay.
And if you guys want like an extra way to review, so the 10.5 and 10.6 stuff, I have those paired X slides on Classroom under the Unit 10 materials. So those were when I did the questions, I had the answers on the next slide. So even if you want to just click through those, but that asks about like, does the mass increase or decrease and why? And then the only other thing besides what's on those slides is looking at cell potential like this. Yep. All right, so if you don't have your notes out, make sure you have your notes out. We're gonna start by talking a little bit about cell potential and free energy. And then we will also look at cell potential and non-standard conditions. So cell potential and free energy, that was on page 9. I'm not gonna talk about everything that I talked about in the video. I'm just gonna hit on some key aspects. And then I'm really gonna spend some time on non-standard conditions because non-standard conditions is probably one of the most challenging parts. It is the most challenging part of electrochemistry because it's all qualitative. So instead of being able to do math, you have to actually think about what's happening. So first, with cell potential and free energy, we look at this key equation. Delta G equals negative N times F times E naught cell. This is on your equation sheet. So on your equation sheet under thermodynamics and electrochemistry, it's on the back. When we had like delta S, delta H, delta G, well, this is another delta G equation. Delta G equals negative NFE. N is the number of electrons that are transferred between the balanced half reactions. So when you make the electrons equal and you cancel them out, that's N. That's your number of electrons. F is a constant. That's Faraday's constant. That is on your equation sheet. You do not have to memorize Faraday's constant. So you just have to know to look on your equation sheet. Really what this equation is this is a way to relate delta G to cell potential. When you have a positive cell potential, you will always have a negative delta G. Well, remember that when we had a negative delta G, we said that the reaction was thermodynamically favorable or spontaneous. Well, if you have a positive cell potential, it's also thermodynamically favorable or spontaneous. That happens in voltaic cells. Electrolytic cells, which we will look at more in detail tomorrow, electrolytic cells always have a negative cell potential. So these are not thermodynamically favored reactions. So they have positive delta Gs. So it's a way for us to relate energy to voltage. When you are looking at energy, you're calculating delta G, I always recommend writing out variables. So write out what is N, what is Faraday's constant, just to make sure you're plugging it in correctly. What is your cell potential? We'll look at this in an example. You'll be able to see how free response questions scaffold. So we go from calculating or writing the balanced reaction to calculating cell potential to calculating free energy. Now, with non-standard conditions and cell potential. So this is what was completely typed out for you on page 10. So you don't need to write all of this down. If you want to, okay, but this is all on page 10. So cell potential, which remember is E naught cell, depends on concentrations or pressures, if we have gases, of reactants and products. So we're looking at how many reactants and how many products do we have, and cell potential depends on that. But standard cell potential, so this naught, this degree symbol, that means we're at standard. So standard cell potentials only apply under standard conditions. Standard conditions is 1 molar if we have solutions and 1 ATM. Well, this corresponds to Q equaling 1. Q meaning the reaction quotient. So when we looked at equilibrium, we looked at Q versus K. Q is 1 because Q is products over reactants. So if all of your products and reactants are 1 molar, Q is 1. But as a cell operates, so as this, for example, as this voltaic cell runs, reactants are used up and products are created because that's what happens in a chemical reaction. Reactants are used, products are made. So concentrations change. As concentrations change, cell potential changes. So as we're using up more reactants and as we're making more products, we would actually see the cell potential change. Now, one question that we see many times is what happens if we change the amount of solid? What happens if we change the size of the electrode? Well, changing the mass of a solid does not affect cell potential because it does not affect Q. So when we are making changes to a cell, we are actually going back to looking at Q. Changing the mass of solids doesn't affect Q, so it doesn't affect cell potential. As long as we have standard conditions, we can use E naught. If we are at non-standard conditions, we have this equation, which is now given on your equation sheet again. They took it off, now they put it back on. This is the Nernst equation. AP does not require you to do calculations with the Nernst equation. They give it to you so that you have it, but you don't actually do calculations with it. We look at it more qualitatively, which is why it can be pretty challenging. When Q is 1, right, when we're at standard conditions and Q is 1, natural log of 1 is 0. So our cell potential equals our standard cell potential. But as Q changes, the cell potential changes because we're no longer at standard conditions. So I put this picture on here because here we have the same cell that we looked at yesterday with aluminum and iron. The electrons are flowing from the anode to the cathode. We have 1 molar aluminum nitrate and 2 molar iron 2 nitrate. 2 molar is not standard. So if we are changing the concentration, we're changing it from standard conditions to non-standard conditions. And at non-standard conditions, the cell potential does not equal the standard. The standard cell potential is what we've been calculating using Appendix E when we're at standard conditions. If we're not at standard conditions, then we have to make some changes. So this is from AP, right? And so this is where we have to think qualitatively. This is from page 10 of your notes. I just shortened everything into some bullet points. So under standard conditions, Q equals 1. Under standard conditions, electrochemical cells, whether they're voltaic or electrolytic, if the cell is running, we are not at equilibrium. As soon as the cell hits equilibrium, it dies because cell potential is 0. So as the system approaches equilibrium, so as the cell gets closer and closer to equilibrium, cell potential is getting closer to 0. So as it approaches equilibrium, cell potential decreases. As the cell runs, we see cell potential decrease because the system is getting closer and closer to equilibrium. In a voltaic cell or a galvanic cell, remember that we always see a positive cell potential. K is greater than 1. Equilibrium constant is greater than 1. Products are favored. Products are favored in a voltaic cell. So when Q is changed, we actually compare Q to 1. If Q is over 1, we are making the system closer to equilibrium because K, the equilibrium constant, is greater than 1. Let's say for some cell, K is 10. So if we make some changes and Q is greater than 1, Q is getting closer to 10. Q is getting closer to K. So cell potential decreases. So if there are two things that you write down somewhere on page 10, here's what I would say. When you increase Q, so you're making some change. You're changing the concentration of products or of reactants. If you increase Q, you decrease E. So when you increase Q by making changes to the cell, you are decreasing cell potential. Then if we go the opposite way, if we decrease Q, right, so when Q is less than 1, for us to be Q equals K, Q needs to be above 1. So if Q is below 1, the cell is further from equilibrium. So it has a longer way to go before it hits equilibrium. And so what happens is cell potential increases. So Q and E are inverse. Now this is for a voltaic cell. If we were looking at an electrolytic cell, it would be the opposite. Typically, we see this question asked about voltaic cells. So if we increase Q, we decrease E. Now here's something that is so important because this is where we see most commonly missed points for questions like this. Electrochemical cells are not at equilibrium. They are not at equilibrium until cell potential is 0. So if you're talking about Q, you cannot use a Q versus K with, oh, the reaction's going to shift to the left or the reaction's going to shift to the right. You cannot use Le Chatelier's principle when you're looking at Q with a voltaic cell. You are talking about Q and comparing it to 1. So when you increase Q, it's greater than 1. You're decreasing cell potential because it's closer to equilibrium. If you decrease Q, that means you're farther from equilibrium, so cell potential increases. These two right here, these are our justifications. Q is either above 1 or below 1. It's above 1, we're closer to equilibrium, cell potential decreases. Your phone, right, your phone or your calculator hits equilibrium when it dies. So when your battery dies, it's not working anymore. It's at equilibrium. So as we get closer to equilibrium, cell potential is going to get smaller and smaller and smaller until eventually it hits 0. So we're going to look at this qualitatively. We'll look at how AP asks some questions with Q and with E. So what we're going to do is we're going to actually do examples 2 through 5. These are all practice AP questions. Now, some of these are going to be extra practice for tomorrow as well. Like for this example, for example 2, A and B, and even C are some good review. So this example is on page 11. Example 2 is on page 11. And A and B look similar to what we saw yesterday with example 1. So we have this Voltaic cell. Before I worry about any parts of the question, I want to label what I know about this Voltaic cell. What is happening, even if we can label the half reactions. So let's take a look at this Voltaic cell. I noticed that they show us the electron flow. So think about, where do the electrons flow? Well, they flow from the anode to the cathode. Another way that we can tell that the left is the anode is because the anions in the salt bridge are oriented toward that side. The anions are in the left side of the salt bridge. The cations are in the right side. Remember, anions in the salt bridge go toward the anode. If you want another review of this, there's a video on the practice playlist that I went through with the particles. And it shows why the anions move one way and why the cations move the other way. What process occurs at the anode? Oxidation. And reduction occurs at the cathode. And so based on that, I'm going to try to just write a general, oh wait, I have the half reactions, never mind. Here are the half reactions. So I see here's aluminum and aluminum 3+ in solution. We know the oxidation half reaction occurs. Well, Al3+ to Al, that's reduction. Because I'm going from +3 down to 0 in terms of oxidation numbers. So if I want oxidation, I want to flip that. So the half reaction that's occurring in this left cell is Al yields Al3+ plus 3 electrons. So there's one of the half reactions. The cathode is reduction, so that's just this reaction is written. Fe2+ plus 2 electrons yields Fe. Now the reason that I labeled all of that is because that's going to be useful in case they ask us more questions about that. Now we have things labeled. So part A says, write the balanced equation for the reaction occurring in the cell. We looked at this yesterday in example 1. We want to take the two half reactions, make our electrons equal so that they cancel, and add them together. So this was our reduction. This was our oxidation, and we flipped the oxidation. So Fe2+ plus 2 electrons yields Fe. There's the reduction half reaction. Oxidation half reaction is Al, yields Al3+ plus 3 electrons. What number can I make both of these electrons equal to? 6. So I'll rewrite this in a different color. So that means I'm going to have 3 Fe2+ plus 6 electrons yields 3 Fe. I'll have 2 Al yields 2 Al3+ plus 6 electrons. So what can I cancel before I add these together? Electrons. That's all that is the exact same. Al and Al3+ are different. Fe2+ and Fe are different. And I'll just add these together. So 3 Fe2+, which is aqueous, plus 2 Al, which is solid. That's 3 Fe, which is solid, and 2 Al3+, which is aqueous. Here is our answer. There is our balanced equation. So we have Fe2 plus and Al as the reactants. We have Fe and Al3 plus as the products. So for part B, determine the standard cell potential. Okay, E naught cell. Calculating the cell potential, we have these half reactions. These are reduction half reactions. These are reduction potentials. The reduction half reaction is negative 0.45 volts. I leave that alone because iron was reduced. Aluminum was oxidized, so since I had to flip the reaction, I flipped the sign. 1.66 volts. So negative 0.45 plus 1.66 is 1.21 volts. Remember, cell potential is given in volts. This is a positive value. That is what we expect for a voltaic cell. Remember that voltaic cells always have a positive cell potential because they are spontaneous. They happen on their own. So number 3, does the concentration of Al3 plus in the solution increase, decrease, or remain the same as the cell operates? Explain. So let's think about what happens as this cell runs. So we have oxidation occurring here. We have Al producing Al3 plus. The electrons go through the wire, come down to the iron electrode, where Fe2 plus is reduced into iron. We have our cation and anion moving in the cell bridge. So as this cell operates, we have Al producing Al3 plus. So as the cell runs and runs and runs, Al is producing Al3 plus. So does the concentration of Al3 plus increase, decrease, or remain the same? You would expect it to increase. Remember, answer the question first and then explain. And if you need to, leave yourself a little bit of space for your answer and do the explanation first. So we'll say the Al3 plus concentration, I'm just using shorthand with brackets, increases as the cell operates because Al3 plus is a product of oxidation. So as the cell runs, Al3 plus is produced during the oxidation. So that's just a question on thinking about what happens as the cell runs. Because Al3 plus is a product, it's being created, so we would expect the concentration to increase. Now, part D, calculate the standard free energy of reaction delta G. Okay, well, again, this equation is on your equation sheet. Delta G is negative N times F times E naught. I always recommend labeling your variables. So I'll just kind of label them over here off to the side. N is your number of electrons that were transferred. It is your number of electrons that you canceled out. So up here in part A, we made both of the electrons equal 6. That is our number of electrons transferred. N is 6. We don't add them together, it's just your number of electrons that were canceled out. 6 electrons were gained and lost. So N is 6. So N is 6 moles of electrons. F is Faraday's constant. That is on your equation sheet. So if you look on your equation sheet, F is 96,485. And the units are coulombs per mole of electron. Coulombs per mole of electron. Coulombs are a unit of charge. Right underneath it tells you 1 volt is 1 joule per coulomb, which is why all of our units end up working out. And then E, we just calculated. So E naught of cell was 1.21 volts. Now we can plug everything in. Don't forget that negative. So negative 6 times 96,485 times 1.21. So negative 6 times 96,485 times 1.21. This is in joules, because a volt is a joule per coulomb. So when I solve for this, I get delta G equal to negative 7,00481 joules. I'll think back to our last unit. What do we typically see delta G given in? Kilojoules. There are 1,000 joules in 1 kilojoule. So we get negative 700. Notice how you have a negative delta G. That also tells you it's thermodynamically favorable. A negative delta G and a positive E cell tell you it's favorable. If you have a positive E, you should have a negative delta G. If not, you probably forgot the negative. And then part E is the value of the equilibrium constant. Greater than, less than, or equal to 1. Explain your answer. Well, if this is thermodynamically favored, it is spontaneous. If it's spontaneous, reactants form products. So products are favored. Products are favored. How does K compare to 1? Greater. So I'm going to answer right up above this. I need to make more space. So we're going to start by saying greater than 1. Start by answering the question. KQ is greater than 1. The negative delta G indicates that products are favored. The negative delta G tells us that products are favored. Any spontaneous reaction, products are favored. Happens on its own. Reactants convert to products. So for this example, A, B, even C, that goes back and reviews 10.5 to 10.7. And then D and E are having us think about delta G. Questions on this example? Galen?
Going back to part D, should that always be negative? Because it's
If E is positive, yes. So for any voltaic cell, delta G should always be negative.
Okay.
When we get into electrolytic cells, you actually have a negative E cell, which means you have a positive delta G. So as long as you have all positive numbers being plugged in, yes, delta G should always be negative because that negative is out front. Yep. Oh, so the 6 moles of electrons. So when you're canceling out electrons, you always need to make your electrons equal. Whatever number you make those equal, those are your moles of electrons that are transferred. And so since we crossed out 6 electrons, that's how many electrons were transferred between the 2 reactions. So that's where 6 came from. All right, so we'll take a look at example 3. This was the longest example. And I have all of the answers in the Do Now slides as well. So if you want to go back and reference these at all, you can. So example 3 is just one question. And this says if the concentration of aluminum nitrate in the aluminum 3+ half cell is lowered from 1 molar to 0.01 molar. And I gave a picture in the diagram over here. What would happen to the cell voltage, so the cell potential? When you make a change, you should look at Q. So we want to think about how it affects Q. So we make a change. Look at Q. Now, for some people, they immediately just say, well, I don't know which one is which. Well, again, we have the electron flow. This is the anode, this is the cathode. So we have oxidation occurring here, which means, I'm just going to draw an arrow, but oxidation means that Al is turning into Al3+. Reduction on the other side is when Zn2+ converts to zinc. So we think about Q. I'm just off to the side over here going to write Q. Q is products over reactants. Remember, Q is calculated like K. Q is products over reactants. Well, I think about what we have occurring here. My products, I said aluminum converts to Al3+, so my products are Al3+ and zinc solid. But I don't put zinc in here. I'll do this and then cross it out just so we remember. Remember, solids and liquids are not in Q or K expressions. My reactants, I start with aluminum solid. And I start with Zn2+ on the other side. Solids are not included. So really my Q is Al3+ concentration over Zn2+ concentration. So if I'm changing aluminum nitrate, that means I'm changing the Al3+ concentration. I'm lowering the Al3+ concentration. It wants to know what's going to happen to cell voltage. So I'm going to leave space for increase, decrease, or remain the same. And I'm going to justify my answer first. So aluminum is the anode. I know because the electrons are flowing from the anode to the cathode. So Al3+ is a product. I'm just going to put this in parentheses, Al to Al3+. I know I left out the electrons, but that's okay. We're just focusing on the substances themselves. So a lower concentration of product will give a smaller Q. Right, over here, if we're lowering Al3+, we're decreasing the amount in the numerator, we're going to decrease Q. Now, here's the most important part. So when Q is less than 1, in a voltaic cell. Now you say, well, how do we know it's less than 1? Well, look, at standard, this was 1 molar and 1 molar. It's 1/1. Now we're not at standard, so now Q is going to be less than 1. When Q is less than 1, the cell potential increases. Because we are farther from equilibrium. So when Q is less than 1 in a voltaic cell, the cell potential increases because it's farther from equilibrium. It's farther from equilibrium because K is greater than 1 at equilibrium because products are favored. This is a spontaneous reaction. So my answer up here is increase. Because remember, decrease Q, increase E. But our justification is that E increases because we're farther from equilibrium. You're farther away from equilibrium, so your voltage is going to increase in order to use up all the reactants. Questions on this one? All right, so example 4. So we have 2 more examples, then you work on mastering. Example 4 is just 2 multiple choice questions. So these are 2 questions that went along with the same thing, so I tried to just put them on the same slide, so I put them as the same example for you. So this is the spontaneous reaction that occurs when the cell at the right operates. Is Ag plus CD solid yields Ag solid plus CD2 plus. So they tell you a couple things here. Spontaneous. Spontaneous reaction tells us it's a voltaic cell, positive E cell, negative delta G. And then they give us the reaction. So they tell us what the reactants and what the products are. The first one says, which of the following occurs if the silver electrode is made larger? So when you make a change, so if you make a change, look at Q. When you make a change to any electrochemical cell, look at Q. So if I write Q for this reaction, this is why it's nice that they gave us the reaction. We can write Q. Q is products over reactants, but you do not include solids or liquids. So products, I'm going to have CD2 plus. I do not include Ag solid because it's a solid. Over Ag plus squared because of that 2. This gives us a little review of calculating Q. So here's Q. Only aqueous and gas can go into Q. So if I make the silver electrode larger, silver electrode is this piece of solid silver. Is solid silver in the Q expression? No. So it's not going to affect voltage. So this first multiple choice question is D. Silver is a solid. Silver electrode is a solid. A solid is not in Q. So the voltage does not change. Second multiple choice question, which of the following occurs if 50 milliliters of a 2 molar cadmium nitrate solution is added? So 2 molar CdNO3 Well, NO3 is a spectator, so really we're focusing here on the CD2 plus ion. So if instead of 1 molar, we change it to 2 molar, it wants to know what's going to happen. Well, if we are increasing the CD2 plus, we're increasing what's in the numerator. We're increasing what's in the numerator. So instead of this being equal to 1, because at standard, the solutions are 1 molar. So if this were standard conditions, Q would be 1. Well, now, Q is greater than 1. Now, Q is 2. Well, remember, when you increase Q, you decrease E. So we know it's not A, we know it's not D, we know that voltage changes, but it still remains above 0. We haven't hit equilibrium yet, because the cell is still running. So the second multiple choice question is B. Because once it hits 0, it's at equilibrium and the cell stops. The cell is still running. It doesn't say anything about the cell stopping. So remember, when you make a change to a cell, look at Q.
Does the change in volume do anything? Like milliliters?
No, because what it's saying is that you're adding it to what you already have here.
Oh.
So either way, I guess technically this isn't exactly 2 because you are diluting this down. So maybe it'd be 1.5 molar instead. So you're still adding 2 molar to this. So you're increasing the concentration.
Okay.
Yeah. Other questions on example 4? All right, let's look at the last example, example 5. So again, we're looking at a non-standard cell. This was part of a free response question a few years ago. So this was just part of a full 10-point free response question. But this is a non-standard cell is made using 0.5 molar solutions of copper nitrate and tin 2 nitrate. So this says the cell potential of this non-standard cell greater than, less than, or equal to the cell potential of a standard cell made with 1 molar solutions. So again, non-standard, you're making a change, look at Q. Now, here's the thing. We don't know what's the anion, what is the anode, what's the cathode. Just look at it as a ratio. Because here's why it doesn't actually matter. You start with 1 molar solutions. No matter what is the product and what is the reactant, you have 1 molar solutions of each. You have 1/1. Q is 1. Well, what happens if you change them both down to 0.5? What is 0.5 over 0.5? 1. The ratio of products to reactants does not change. So I'll use this one. So for part A, so we're looking at cell potential. So it's actually equal to. Make sure you're answering the question at once. You should start with greater than, less than, or equal to. So the cell potential of the non-standard cell is equal to the standard cell. I'll say in both the standard and non-standard cell, Q equals 1. I'll do 1 molar over 1 molar and 0.5 molar over 0.5 molar. It doesn't matter whether Cu2 plus or Sn2 plus is the product or is the reactant. You're looking at the ratios. The ratio of both of them is 1. So since they're both Q equals 1, they're both the same cell potential. And then for part B, both the standard and non-standard cells can be used to power an electronic device. Would the non-standard cell, so this is the one that is made from 0.5 molar solutions. The non-standard cell is made from 0.5 molar solutions. Would it power the device for the same time, a longer time, or a shorter time as compared with the standard cell? The standard cell is made with 1 molar solutions. So I think that when a lot of my classes read this question on the free response, they were trying to make it some big calculation. This is nothing more than thinking about a chemical reaction. Kind of think about it in terms of kinetics. Which one of the cells, the non-standard or the standard, has more stuff in it? Standard. The one that has more stuff is the one that's going to last longer. So we're comparing the non-standard. It has less stuff, right? I keep saying stuff, but it has less reactants. Less reactants means it's going to run for less amount of time. So for part B, the non-standard cell will power the device for a shorter time compared to the standard. I'll say the supply of reactants in the non-standard cell is less. So it will run for less time. So the less reactant that you have, the less time it will run. The more reactant you have, the more time it will run. When you change conditions, always look at Q. Remember, this is not a Le Chatelier argument. This is a compare Q to 1. When you increase Q, you decrease E. Because when you increase Q, you're above 1, you're closer to equilibrium. And so cell potential is going to be lower. You hit equilibrium when cell potential hits 0. Questions on this example? Okay, so you have this at the bottom, right underneath example 5. So this is just kind of a summary of non-standard conditions. This is a challenging topic on the AP test because it's all conceptual. So I gave you here essentially what we've been talking about this entire time. When you increase Q, you decrease the cell potential. When you decrease Q, you increase the cell potential. You do not want to use Le Chatelier's argument because the cell is not already at equilibrium. The cell is still running. The reaction is still running. When you change the mass of solids, it doesn't affect cell potential because it's not involved in Q. So you have some time to work on mastering. Same thing as yesterday, 1 through 5, 6 through 12. These will be a good review for tomorrow because the quiz tomorrow will be 10.5, 10.6, 10.7. Then you can go through 10.8 as well. I have all of the questions labeled by video. But then after the quiz tomorrow, we're also going to work through examples with 10.9. So 10.9 is already up. If you'd rather watch 10.9 right now, get that out of the way. That should already be up in classroom. But then you just have some time still to work.